Okay. Now I'm going to have to move like lightning to get over there, and I don't want the sonic boom to disturb anybody. So I'm going to get over here so I can go a little bit subsonic and get to the end without blocking it and all that stuff. Okay, so it comes in here, goes down there, gets stopped nicely. Okay, that was kind of an interesting thing that happened there. Look at what happens to this pile of chalk. Well, it kind of glanced off the distance. There was a double collision. And we'll worry about collisions later. Okay, there's enough that we're laying on you right now. Now, two things. I think this will be stable. How long does this take to get down to the end? I want you to make your own judgment. Just count 1,001, 1,002, whatever. Okay. Make your best estimate of how long that took. And the distance was 60 centimeters. Actually, I take it back. The distance is about 90 centimeters. Okay.
90 centimeters.
Yep, that's 3 feet. Yep. It's actually like 90.8 or something like that, or 91.8. It's close enough. Okay, so 90 centimeters. The thing went 90 centimeters from rest. I think the mass of this thing is about 0.05 kilograms, might be 0.06. Got a electronic balance over there I can find out, but we'll just go with 0.05 because it's an easy number to deal with. Okay. So we're going to get the final velocity, final kinetic energy, work by the net force, and answer the question, did you do the assigned problems? I think I asked you to send them to me, I only got one set. They're on the assignments page. So if you didn't do them, you're going to be in worse shape to understand what we do today, but we'll go over these. Okay, I wasn't recording, but all I've done is said that, okay, you want to find the final velocity, you've estimated the time it takes. So you have a time between what we call T naught and T. I'll put a graph of velocity versus time. Graph is a straight line. At least that's what we assume. That's what I expected you to assume. Because if it isn't a straight line, you're not going to be able to solve the problem at this point. You don't have enough data. So we're going to assume a straight line because it's reasonable to do that because this is a straight ramp. And you'll understand as we go through the course why that is. Okay, so now I've got some time delta t between here and here. And that's what you were going to estimate. So how do you get the final velocity? Well, it's pretty obvious that you want to divide how far you went, which I'll indicate by delta S, change in position. Could be a delta X if you're moving along an X-axis, okay? Would you rather see delta X?
I would.
Yeah, some people would, some. Hopefully you'll get less notation dependent as we go through the course, but at the beginning, everybody tends to be pretty notation dependent, even though most of you have had a year of engineering. Okay, so I'll call it delta X. So delta X over delta T is 90 centimeters over. Let's just say delta T was 3 seconds. Okay. So let's say we estimate delta T equals 3 seconds. My estimate was 2.7 seconds, but who wants to divide by 2.7? We'll divide by 3. Some people had 2.5, and that would be good too. All right. So anyhow, we have this, and that's 30 centimeters per second. Well, that's the first thing you're going to do with your data. Okay. Now, what does that 30, where does that 30 centimeters per second appear on this graph? Well, this is the average velocity. I'll specify V sub av for average velocity, but a lot of times we'll just call that V bar. It's a standard notation for an average of a quantity of a bar with the top of it. Okay, but it doesn't hurt to use subscripts. So that's the average velocity, it's 30 centimeters per second. Again, where does that appear on the graph? Well, that's the average velocity. It's not the initial velocity, it's not the final velocity, it's the average of the initial and final velocity if the velocity graph is a straight line, velocity versus time, which means that 30 centimeters per second is going to occur at the midpoint of this interval. And I got it a little too far to the right, but you understand that that's your average velocity. And your final velocity, which is what you're going to want for the final kinetic energy, is not your average velocity. Your average kinetic energy isn't even the kinetic energy you get from the average velocity because you're squaring the velocity. Okay, what's a square of a half? It's a fourth. If you use the average velocity to calculate your final kinetic energy or your change in kinetic energy, you don't have 1/4 of the correct answer. And you want to kind of ponder that idea. You want to understand those proportionalities, and that would be a good thing to think about. But the point is that your final velocity, since the initial velocity is 0, well, okay. Now, I never want you to use this without specifying somehow that the velocity is a linear function of t and the initial velocity is 0. Okay? I find it all the time. People memorize equations and use them when they aren't appropriate. It's a very inappropriate equation to use, except under special conditions. That you have a linear velocity versus time, and either your initial or final velocity is zero. Okay. This would have worked just fine if the thing had been gone uphill and come to rest right here after 3 seconds. In that case, the graph, without going into all the detail, would have looked like this. Okay. And your average velocity would have been right here. And your initial velocity would have been here because the final velocity is zero. Okay. So either the initial or final velocity is zero. And the velocity changes linearly with time, meaning that you have uniform acceleration, because that's what it means for velocity to be a linear function of time. Okay. You can apply this. Final velocity, we double your average velocity, or maybe it's the initial velocity, it's double the average velocity. One case where you would use the latter is in lab. We're going to be observing a good friend. Okay. And we're going to let it come to rest. And then assuming that you have linear velocity versus time, we're going to determine how fast it was rotating at the beginning. And maybe how what the kinetic energy of each magnet was. Okay. And that's easy to calculate if you know a little bit of geometry and circuit, some facts about circles, and hopefully understand radians. All right. Well, we'll do that in detail, but make sure you get it before you come in to the next class, right? We don't have lab. We have lab Friday, right? Talked about that previously. So we're going to be observing these things. We're not going to be able, when we observe it, to determine whether the acceleration on this ramp is uniform. But we will be able to make observations of the angular motion to determine whether the angular motion has a uniform omega versus t. Omega is what we use instead of v. And you've seen that already. You should be familiar with that notation, or at least it shouldn't throw you for a loop at this point. Okay, it's the rotational equivalent of your velocity. Okay. And usually we find that it's not quite uniform, pretty close. Then we talk about how to adjust for that and do the integrals. Okay, we'll do that. We'll do all that in lab. So if you have all the integral stuff down, and a lot of you wrote some integral stuff that was appropriate, okay, then you'll be good with that. All right. Well, anyhow, you find the final kinetic energy. The rest of this is pretty straightforward. So the final kinetic energy . Okay, what's the mass? Now we actually want to work in SI units. If you read through the first couple chapters of your book, like I asked you to, you at least know that we have SI units, kilograms, meters, and seconds as far as we're concerned right now. Okay. I also mentioned in the assignment that I gave you, I was careless. I wrote down incorrect units in some of these problems. I ought to go back and look at the units I used and see where I screwed up. I'm not going to change it. Probably put a little note there. Look out. I typed too fast. I created that entire problem set from the document I used. I ran a program on it that I've written to randomize it. So we got 10 different versions of 10 different sets of numbers. Okay. So I wrote those problems in the code that I need to run the program on, generated it, put it into HTML format, all in 45 minutes. So it's still a real bonehead error that I made on the units, but it's a bad error. So don't believe the units. All right. Anyhow, so you do want to do that. Okay, anyhow, the mass is 50 grams or 0.05 kilo. I gave you 0.05 kilograms. And VF is 60 centimeters per second squared. Well, that multiplies out. I mean, that's 3,600, right? 60 squared is 3,600. And then you take half of 0.05, which is 0.025, which is a 40th, which is 900. Kilograms, centimeters squared per second squared, right? Now that's not SI because centimeters per second is CGS unit instead of an NKS unit. Okay. But a lot of the stuff we do in lab gives you nicer numbers if we use grams and centimeters rather than kilograms and meters. So sometimes we'll do that. So we have to know how to convert it. Well, it's easy to convert. It'd be even easier to convert if I had this thing completely within the view. Okay, so here we have it. Now, textbook gives you methods for conversion, probably see methods for conversion in your engineering classes and so forth. But a centimeter is 0.01 meters, so I can replace a centimeter by 0.01 meter. And square that. Well, this thing doesn't collapse on me, it all weighs all 40 pounds. And it's seriously injured. Point 0.01 meters squared is 0.0001 meters squared, right? And that's 0.09 kilogram meters squared per second squared. Like that's 1/10,000, so like 900 divided by 10,000. You visualize those numbers, you see it's less than a tenth. So the 0.09 makes sense. It's good to be able to do that. Okay. Now I'm going to introduce, anybody know what you call a kilogram meter squared per second squared?
Joule?
Yeah. Somebody out in the hall calling someone named Jewel.
No, must be.
Yo, Jewel. Okay. No, you stop that out in the hall. Okay. When we're recording. Okay, now. So I'm just going to put a J down for Jewel, but you've seen that if you've read it. Okay. Say if you knew it when you came in or you read it, either way, whether in your cap. Now, if you'd have said Geraldine, I'd have probably had to trash the whole video because somebody might have identified you and made fun of you because of that. And you couldn't handle that, could you? No, not at all. Okay. So there we have it. Any problem with that? I don't think anybody's going to have any problem with that. From what I've seen might clarify a few things for you. Might be a little bit of new information, but I think people are in pretty good shape here, and I'm happy about that. Okay. Now, how much work then was done by the net force? I'm going to pause this thing. Okay, well, we just determined that the change of kinetic energy. Well, what is the final kinetic energy? Okay, Well, we've now determined that according to my estimate, the final velocity was 60 centimeters per second. So I'll just note that here. In the final kinetic energy, .09 joules. What's the work by the net force? The most important. Well, I mean, there are a lot of important things like Newton's second law. Net force is mass times acceleration. Right? People should be kind of familiar with that. And we'll use it. We're going to bring it in here. We're going to try to figure out the net force. Some of you did, I think. That's good. Make sure that camera is willing to pick up everything. Close enough. Okay. Okay, so we're talking about what's work by the net force. Well, there's a name for this. It's the work energy theorem. Net work by the net force is a change in kinetic energy. It's also equal to the integral of the net force with respect to position. I don't put the limits on this integral, just indicating it put appropriate limits in that integral, and we'll see how to do that. It's easy enough. We'll actually do that, okay? So work by the net force is equal to the change in kinetic energy, also equal to the integral of the net force with respect to position. And actually, that's a vector equation. But you don't know how to interpret that vector equation yet. Maybe you do. If you have molar variable calculus, you better. But otherwise, probably not. Okay. Anyhow, work energy theorem allows us to answer this question really easily, right? Okay. Now, did you do the assigned problems? I don't know that everybody answered that. I didn't look. But obviously did something because everybody knew something. Okay. So, so you've obviously haven't been sitting on your thumbs, and very glad to see that. That's fatal. Okay. Don't want anybody dying. Now, we understand that. So, question now, I didn't ask. What's a net force? Well, there are two ways to answer this question. Net force is mass times acceleration. Okay. What do we know here? Well, we know the mass. What's acceleration? Somebody want to tell me what acceleration is right after I pause? Okay, very quickly got an excellent answer that the acceleration, well, there's a caveat here. If you need another V in there, V versus T is linear, then acceleration is delta V over delta T. Okay. That's ROC standing for rate of change of velocity. WRT meaning with respect to T. Okay. Another abbreviation I use fairly often is looks kind of like that, but it's WTF. Okay, you know what that stands for? It's actually got a question mark on it. You answer, what's this foolishness? Okay. Now, some people use a different expression that isn't even grammatical. Doesn't make sense, even though the intent's fairly obvious. Okay. An expression of confusion. It has nothing to do with foolishness. Anyhow, that's something to blazon upon your memory with all the conditions, not just a formula to remember. Formula that only applies to acceleration's constant. And V versus T is linear. Okay, that's actually not and, because V versus T being linear means exactly the same thing as acceleration is constant. Okay. Now, I don't know if this is still visible. It is. We could calculate the acceleration on this graph, and it's important to be able to visualize that. Because, of course, if acceleration is a rate of change of velocity with respect to time, if V versus T isn't linear, but if you know the function for V, you can find the function for acceleration. So let's just discuss that for a second. If you got the function for velocity and acceleration is a rate of change of velocity with respect to time, what would you do to get the acceleration function? Okay, I was hoping for a good answer, and I got one. Now, if the velocity is a function of time, then the rate of change of velocity with respect to time is the derivative of that function with respect to time. Okay? Okay. And we say with respect to time because velocity is also changing with position, isn't it? If you take the derivative of velocity with respect to position, that'd be something completely different. I'm not going to confuse you with that right now because it is a little confusing. Okay, but we will later when it isn't so confusing. Okay, so how you do that on the graph? Well, you just take any 2 points on the graph and you make a right triangle. One side's the run, the other side is its rise. Slope is rise divided by run. But the run equals a time interval, and the rise equals a change in velocity. Now, I was going to do that between these 2 points of the graph, but I'm changing my mind because I want to use delta t for the run, and I've already called this interval delta t. So I'll leave this here. And I'll do a big blue triangle. Okay. So I could do run equals and I could do rise equals for the small triangle or for the big triangle. So I'll say the slope is rise over run for the small triangle, but that equals the blue rise over run. Nobody's colorblind on it. Okay. My point is that each triangle has a rise and a run. I don't know exactly what the time is here and here, so I'm not sure what the run is. But I do know the run here is just PF9 minus T naught, which I call delta T. And the rise is VF minus V naught, which is just VF minus 0. Can you read that? Okay. So that equals now that might be a little harder because blue can be a little bit hard to read, but it is VF minus V naught over TF minus T naught. Okay. Since the initial velocity is 0, VF minus V naught is just VF, right? So I can just note that this is equal to VF. And that's a special case because your initial velocity isn't always 0. And your final velocity is not always 0. But in this case, there we have it. Okay, well, we can see that as the slope of a right triangle, but it is delta V over delta T. You should have written that up here. That's delta V over delta T, which equals this and so forth. So in any case, the acceleration for my estimate is 60 centimeters per second over 3 seconds. Which is 20 centimeters per second squared. And I'm not sure the camera's picking up quite all of that. Pretty close, but okay. Okay, everybody understand that? We'll be able to use that to solve problems. I think you will. Because you showed pretty good problem solving ability. Okay. Now, of course, we're trying to answer the question, what's the net force? So just jot it down on your paper there. How are you going to get the net force now that we've calculated the acceleration? So you can just do that calculation in the next 60 seconds. Let me just double check, make sure everybody's on track, okay? Oh, I didn't say any of that. Well, I'll just do it real quick. I think what I said, I think we've seen that if you do MA with 0.05 kilogram to 20 centimeters squared, you get this and so forth, and that gives you the 0.01 in a Newton is a kilogram meter per second squared. And I think what I've done then is come over here and said CGS units in that force is still in units of mass times units of acceleration. But unit of mass is a gram, the unit of acceleration is a centimeter per second squared. So gram times a centimeter per second squared is what we call a dyne. And then we can just go right over here and compare a dyne to a Newton because it measures the same thing, but it's a small fraction of a Newton. Okay, so a dyne is a gram centimeter per second squared. Now there are various ways to do conversions. I'm just going to replace gram with 0.001 kilogram centimeter with 0.01 meter and do the arithmetic. And I get 0.00001 kilogram meter per second squared. That's 10 to the negative fifth, and that's a Newton. Okay. And I mentioned that you could feel a force that small, okay, with your fingertip or something, or your eyeball, or your tongue, okay, maybe. An erg is what? Well, your work is in units of force times distance. So that's, in this case, all the way over there, where I never did calculate, well, yes, I did. And I calculated on another board, okay? It was in kilogram meter squared per second squared, okay? Because kilogram meter per second squared. It's kilogram times a meter per second squared, okay? In CGS units, it's a gram times a centimeter per second squared. And I didn't say all that. It is in kilogram meter squared per second squared. We're talking about joules. My eye caught force and I started talking about force. My eye just does that. I'm sorry. Okay, so net work was 0.09 joules, and it wasn't F equals MA. It was force times distance. So we have to multiply this by distance. To multiply this by distance, you get another meter. So it's a kilogram meter squared per second squared. In CGS is a gram times a centimeter squared per second squared. It's analogous to the way it was done there or here. We see it's a gram centimeter squared per second squared. Place a centimeter by 0.01 meter, then gram by 0.01 kilogram. Do the arithmetic, you get 10 to the negative seventh kilogram meter squared per second squared, kilogram meter squared per second squared, joules. Okay. And this is an important system of units. As I said, when I thought I was being recorded, this is a tiny unit of energy, but I would think if an erg of energy went off in your eyeball, you'd see a pretty bright flash. Okay. And I did mention that in some engineering applications, thermodynamics, you're measuring energy in ergs because that's the more appropriate unit for a single molecular interaction. Okay. It's a lot of ergs. I mean, it's a small fraction of an erg, but it's an even smaller fraction of a joule. So it's easier to think in ergs. So just use the system that you think in. But in this course, not totally exclusively, but fairly exclusively, we're going to use SI units. But sometimes when we measure things in lab, we're going to have things in centimeters per second, like we did with the ball rolling down the incline at the beginning of class. And we'll need to make sure we get that into the appropriate SI units. Okay. Okay, I'm going to start this thing spinning, stand back so I don't take my chin off. Yeah, it's still spinning, but magnet turned upside down and everything. What the heck? Put the magnets back on, spin it again, 1001, 1002, okay. It's gone more than half a revolution in a second. Okay. That's about half a revolution per second, okay. So it's moving about half a revolution per second. These magnets are about 50 grams. Okay. So at half a revolution per second, now this is 60 centimeters long. Can you give me an estimate? What would you do to estimate the kinetic energy of this magnet? Here's the situation. Piston's moving at half a revolution per second. What's the kinetic energy? Of a magnet? According to what you estimate and what you saw, right here's the system, there are the two magnets. What do you need to estimate in order to start answering the question? Okay, the reasoning that we're getting here is, you want to know how far it moves, okay? Or whatever, how far a magnet moves. There is a question, do both magnets move the same distance in the same time? Well, one of them's closer to the center than the other, so one's going around a bigger circle than the other. So obviously one of them is going faster than the other, so one of them's going to have more kinetic energy, right? Make sense? Yeah. Okay, so what estimate would you start with? That was my original question. What would you want to estimate in order to answer the question? Revolutions per second, angular velocity, right? That's omega for everything on that beam, okay? At a distance of 20 centimeters, it's 0.5 revolutions per second. A revolution per second is 2 pi radians per second. If you don't know the 2 pi radians in a revolution, go back and start reviewing your crib. Okay? Or learn it if it wasn't taught, and I hope it was. So that comes out pi radians per second. So its speed is omega r. And follows that the kinetic energy is easy. Okay? Now, why is V equal to omega r? It's because of the definition of a radian. And I'm just going to state this so we can get out of here, but understand why V equals omega r in terms of the definition of a radian. Get that straight. You can ask AI if you want, you can look it up, but make sure you understand it Friday. They're going to be dealing with both motion along the ramp and revolutions, rotational motion. Okay. I also recommend that you work out the kinetic energies of those two magnets according to your estimates. Because you're going to be needing to do that. And we don't want to get hung up on that in lab. I don't have to explain that again because there are things that we want to do in lab. Okay. So make sure you do that. And if you don't, if you have trouble doing it, send me a picture of whatever you're trying to do. Or write out a good question. Not how do you do it, but here's what I understand. Can you get me a little further along? Those kind of questions I can answer efficiently because I can focus on what you need to hear. The question is, hey, how do you do that problem in the homework? Don't even tell me what the problem is. I've had questions like that. Matter of fact, I got one this morning. And I'm polite. I just say, yeah, could you maybe tell me which homework it is and what problem? I didn't even say it that way. I said, I'd be glad to answer. Can you tell me what the homework was and which problem it was? So I can look it up. Okay. So in other words, give me the right information if you ask me a question. Do your best, because that's an important skill to be able to ask the right question. It's also important to be able to ask AI the right question. I answer differently than AI, but I at least understand what I'm saying, whether it's right or wrong. Okay. There you have it.